talk is by Hongfei Fu. I'm going to talk about automated recurrence analysis for almost linear spectra in bounds. Okay. So in this talk, we consider running time for randomized algorithms. So in many cases, in randomized algorithms, worst case analysis is not so useful because we consider the expected runtime behavior of those algorithms. So in this talk, we consider average case or expected runtime analysis for those randomized algorithms. And for those behaviors, we normally have manual analysis, and such analysis is very cumbersome and requires manual mathematical proofs. And so in this talk, we consider automated techniques for those problems. So here we consider recurrence relations. So why we choose this? Because it is a very simple representation for the running time behavior of those algorithms, and it's also manually derivable from those algorithms. And there are several previous results which use various techniques for solving recurrence relations. So first we have for worst case analysis, so we have different equations, Euclidean functions, generating functions, and also finite linear recurrences. And for the average case analysis or for expected runtime things, we have also have different equations and also have generated functions, and we also have several other approaches. And also we have proof rules and martingales. And here we consider average case analysis of univariate recurrence relations, and we consider only an almost linear asymptotic behavior of those recurrence relations. The motivation is that many randomized algorithms have almost linear asymptotic behaviors, and we also consider tight complicit bounds for those recurrence relations. And so we consider a syntax for our recurrence relations. First, we have recurrence expressions, which encompasses first paths for non-recursive algorithms, and we have normal recursion. We have divide and conquer, and we also have randomized index selection, and we also have simple arithmetics, which corresponds to simple composition of algorithms. And then we'll have that recurrence relation is just a pair where we have a base case and also an inductive case, and then naturally we can define a solution for such a recurrence relation which corresponds to the running time behavior of this recurrence relation. So we have an example which is a randomized version of the binary search algorithm, which is called Sherwood's randomized search. We have this recurrence relation which corresponds to the expected runtime behavior of this algorithm. And then we use guess and check functions, which is popular because usually we guess the function and check whether it satisfies certain conditions. If yes, then this serves as an upper bound on the average case behavior of these algorithms. So we have the definition for guess and check functions. So first we have base condition, which say that from within a threshold, a finite threshold, the running time of this recurrence relation is no greater than this function, and from the threshold and from the threshold we have this inductive condition holds, which says that by substituting this Gaussian function into this recurrence relation, we obtain that this recursive inequality holds, which says that the expression under the substitution of this function is smaller than the function itself. And then we have the theorem which says that if we have such a Gaussian function, then this function serves as an upper bound for the every case of expected runtime behavior of this recurrence relation. So we synthesize Gaussian functions to obtain upper bounds on the every case behavior of recurrence relations. So first we have templates. So here we can only very simple templates, which is almost linear, where D is an coefficient to be synthesized, and we have the Gn is very simple. It reflects almost linear behaviors, and the C is a constant, and here we simply choose it as the base step of those recurrence relations. And then we employ techniques to solve the coefficient for D. And here we use over-approximations for logarithmic terms, and we also perform very simple coefficient checking between polynomials, but extended with logarithm. So let's take a very simple look at the over-approximation we use. We use over-approximation for unbound summations of logarithmic terms. So for example, for this summation from 1 to n minus 1, the summation of log j. So we over-approximate it with an integral expression. So here we can see that this over-approximation is not trivial because it over-approximates this summation within a constant shift. So we can easily have the integral from 1 to n of log x to be an upper bound for this summation, but we make it even closer to a constant shift. And then we have this coefficient checking, which says that we can check whether there exists a D such that D multiplies P is greater than or equal to Q for sufficient larger n, where P, Q are two polynomials. We can do this by checking the several conditions on the coefficients. So we take an example. So we take this Sherwood randomized search, and first we have a template where here we choose this to be a simple logarithmic template, which is D times log n plus 1, and then we need to plug in the approximations for the right part of this recurrence relation. And the core part for over-approximation is to over-approximate this summation, and we plug in the previous theorem we saw, and we obtain that the over-approximation is like this expression, and then we plug in this over-approximation into the inductive condition for Gaussian functions, and we obtain this form, which is some D times P greater than or equal to Q, and this should hold for sufficiently large n's. So, and then we do coefficient checking. So we see that the leading coefficient at the left part of P at the left part of this equality is 1 minus log n, 1 minus log 2, which is positive, and And we also see that the degree at the left part is no less than that of the right part. So by a theorem, we can conclude that there is a real number d which is positive, and that this inequality should hold for sufficiently large n. And then we can safely conclude that the asymptotic behavior of this algorithm is logarithmic. So we also considered several bivariate cases. Where a bivariate case is a recurrence relation where we may have two variables. And we do this by a simple reduction into univariate case. So for example, we have this famous example of coupon collector, which collects a coupon until it collects all types of coupons. So we have so we can build a two-variable model for this example, and we have a two-variable recurrence relation, and we can safely eliminate so we can safely eliminate the appearance of n, and we can obtain a recurrence relation with only one variable. So now we consider tight commutative bounds for recurrence relations. So the motivation is that in some cases we need to know very tight bounds for the expected running time behavior of some randomized algorithms. So in those cases, when we only have asymptotic bounds, it's not enough. So we build our approach on our first one for asymptotic bounds. So we first obtain the inequality d times p is greater than or equal to q from coefficient king in our analysis for asymptotic bounds, and then we calculate a threshold n which is large enough, and then we associate a small enough epsilon for this n, and then we output the value d as the least number, which satisfies these two conditions. So the first condition is called is finite saturation, because we require that before this threshold, the running time should be no greater than d times h. And we also have this limited situation, which is derived by taking the limit n tends to infinity, and we obtain that d should be greater than or equal to this number, and there is some coefficient things there. Where we have that Cp as the leading coefficient of P, and Cq is the leading coefficient of Q. So let's take an example. So we have so first we choose epsilon to be 0.9, and we calculate n to be 6, and then we see from finite saturation that this d should satisfy those inequalities. And then we also have this limited situation, which also provides a lower bound for d, and we find that d can be chosen to be 204.535, and we obtain a logarithmic Gaussian function, and somehow we see that this coefficient is too large, but once we choose epsilon to be 0.01, we obtain a very good value for d, which is 19.762, which is very good. Since we can prove that the optimal value lies between 15 point something and 19 point something. So we perform experimental results on several very famous randomized algorithms. So we have Sherwood randomized search, we also have quick sort, quick select, and we also have diameter, which is a randomized algorithm for calculating the diameter of a finite set of three-dimensional points. And we also apply to an example which integrates sorting with quick select. And we also performed experiments on several bivariate case analysis. And the experimental result is quite good. We obtained, so in every case, we obtained optimal bounds for those algorithms. And then we also obtained quite tight bounds for the every case or for expected runtime of those algorithms. And our algorithm or our approach is quite efficient because for every example, our algorithm runs within 0.02 seconds. So, in conclusion, we applied several new approaches to analyze the expected or average case behavior of randomized algorithms. So we target recurrence relations, and then we obtain asymptotic behaviors through guess-check functions and several techniques. And then we even get very tight bounds for the complicit analysis of those algorithms. And in the future, we plan to first explore the transformations from those randomized algorithms into recurrence relations, and we also plan to explore efficient approaches for complicit bounds of higher degree. For example, this n squared log n. And this is all my talk.
Questions? So I have a question. What is the connection of your analysis with the smooth complexity analysis by Spillman and Tang?
I think it's a bit different from our case because smooth analysis is randomization over the inputs. So here we focus more on randomization in the algorithm. So I think this is the difference.
Other questions? Okay, let's thank the speaker again.